loves electronics. In this video, we are going to learn how to use Norton's theorem to find solutions to circuit problems. We are going to learn how to find the IN, which is the Norton's current, Rn, which is the Norton's equivalence resistance, and also use the Norton's theorem to find the current that is flowing through resistors, let's say load RL. So, according to the Norton's theorem, any linear circuit connected between two terminals can be replaced by a Norton's current in parallel with the Norton's resistance. So, in between two terminals, any linear circuit can be replaced by the Norton's resistance, equivalent resistance, the Rn in parallel with the Norton's current, In. So let's just say that we want to find the current that is flowing up through a resistor RL connected between the two terminals. We are going to use the current division rule to find the current that is flowing through the resistor RL, which is going to give us, let's say if the current flowing through RL is I1, is going to be Rn divided by the RL plus Rn, using the current division rule, times the In, which is going to give us the current that is flowing through the load RL. So basically, this is how the Norton's theorem works. Without wasting my time, we will take one question and then we'll use the Norton's theorem to find the current that is flowing through a resistor. So let's just say we have this question. So we want to find the current that is flowing through this 3 ohms resistor. Now, we are going to use the approach that we have over here to solve the Norton theorem questions. So the first thing that we do is that we remove the resistor RL and mark the terminals. So we want to find the current flowing through this resistor. So what we are going to do is we are going to remove this resistor and then mark the terminals. So after removing the resistor, we are going to have the circuit in this form. So that's the first thing that we have to do. Then the second thing that we do is that we find the short circuit current IN. So we are going to put a short circuit in between the terminals and then find the IN, which is the short circuit current in the short circuit. So this is how it's going to look like. So we are going to, with the direction of the current, you can choose to assign it either ways. You can choose to make it go in the right way or the left way. But for the purpose of this video, we want to choose one and then use it to solve our question. So let's assign current over here. The positive terminal for this voltage source is going this way. So let's say the current over here is going this way. Then there is another current that is coming that way. So if we are using KCL, we know that the current here, if the current over here is I1, the current over here, according to KCL, is going to be the IN plus the I1. We are going to use KVL to find the current over here. So if we take this loop, we are going to have 42 to be equal to 12 IN plus I1 plus the 6I, which is going to give us 42 to be equal to 12 IN plus 18 I1. Then we are going to take this loop also. So when you take this loop, we are going to have 35 to be equal to 6 I1. So the I1 is going to be 35 on 6. Once we have the I1, we can do a substitution over here to find our IN. So our IN will be 42 minus 18 I1 divided by 12 to be our IN. So our IN is going to be 42 minus 18 times 35 on 6 divided by 12. This is going to give us minus 21 on 4 as our IN. So after we are done finding our IN, the next thing that we have to find is our Rn, which is our Norton's equivalent resistance. So with that, the first thing that we have to do is we have to deactivate all sources. All voltage sources should be short-circuited and all current sources should be open-circuited. So for this particular question, we only have voltage sources. So we are going to short-circuit the voltage sources. So the equivalent circuit is going to look like this. Having the terminals. So one thing that you realize is that the 6 and the 12 are in parallel. So our Norton's equivalent resistance is going to be the 12 in parallel with the 6, which is going to give you 4 ohms. So with all this in place, we are going to draw the Norton's equivalent circuit, which is the current source, our IN, which is minus 21 on 4, in parallel with the Rn that we got before, then in parallel with the resistor that we wanted to find the current across, which is the 3 ohms resistor. So just like we discussed earlier, we are going to use current division rule to find the current through the 3 ohms resistor. So if, let's say, the current through the 3 ohm resistor is I, so I should be equal to IN times Rn on 3 plus Rn, which is going to give you minus 21 on 4 times 4 on plus 3. So this, which is going to be minus 21 on 7. So the final answer is going to give you minus 3 amps as your answer. So the current through the 3 ohms resistor is minus 3 amps. So that's how we use Norton's theorem to find the current flowing through a resistor.